Hi, welcome to the Vector Code Quality Symposium 2024. I'm Jason Masters and I'm a Senior Field Applications Engineer at Vector. And today I'm going to talk about breaking coding standard rules. I'm going to describe when you're allowed to break the rules and how this must be done in a safe, controlled manner. And then we're going to look at how you do this practically with the static analysis tool and how we report on the code compliance. Why are breaking the rules allowed? Then we're going to look at breaking the rules, a process for breaking the rules. Then we'll have a look at how we can do this using static analysis and deviations. We'll have a slight diversion into talking about legacy code. And then we'll have a look at how we can report on our code compliance. And then we'll have a very short demo and then a summary. Just a quick note on terminology. Most coding standards have things like rules, guidelines, and directives, different categorizations of rules. In this presentation, I'm just going to use the word rule to make it nice and simple for me. So why do we break the rules? Why is breaking the rules allowed? If we have a coding standard that has rules, why are we allowed to break the rules? Well, we may have compiler-specific behavior, for example, bit field types, where embedded compilers allow bit field types to be of non-standard types. And this usually allows for better alignment and access. There may also be completely non-standard types, such as a bit type. Using these extensions improves the efficiency, both in terms of memory and speed, but they essentially break coding standard rules. We may also have interfaces to third-party code. We might use a third-party library, and we're constrained by the provided interface. For example, declarations that use implicit int or use KNR function declarations, and we can't get round using those. We may have legacy code, where code that we want to put in our project has not been written to a coding standard, and we are reusing that code in a project that attempts to comply to a coding standard. And this is very common. Software projects rarely start with a completely clean sheet and usually involve some degree of reuse. And we'll talk about this topic more later. We may also have variant code. Our code base may be applicable to a number of devices. And so we may have code that may be activated for certain variants of code and not activated for others, leading to unreachable code or code where conditions are always true or always false. If we're writing for an embedded device, we're probably going to read and write to registers to access memory and peripherals. And this involves usually reading and writing to fixed addresses, which means converting an integer to a pointer. We may also have areas of memory that are not declared as an array type, but we access like they were an array type. And again, this breaks coding standard rules. We may also have some degree of auto-generated code in our project. And also code generators are unlikely to make the same mistakes that people make. So code rules that apply in that area are not necessarily needed for auto-generated code. Also, auto-generated code is unlikely to be reviewed by people. So some of the rules that make code clearer and easier to understand, for example, using octal constants or using identifiers that look similar, we don't really need those in auto-generated code. And as a side note, Misra has generated a number of permits that cover a lot of these common cases to make generation of deviations easier. But just because those permits exist, it doesn't mean you're allowed to use them in any context. You still have to employ the same due diligence you do for deviations if you are creating the reasons yourself. They just make it a little bit easier. So can we break the rules whenever we want? Well, no. Just because you can break the rules, it doesn't mean you should break the rules. Perhaps when it's easier to write code that breaks the rules than it is easier to write compliant code, or where there are compliant alternatives. If we have two choices of writing some code, one that breaks the rules and one that doesn't, we should always choose the one that doesn't break the rule first. And we should also appreciate the wider context of breaking the rule. Look at the spirit of the rule, not necessarily just the letter of the rule. And we should also have the approval of a competent person who's assessed the impact of breaking the rule and the impact of the alternative code that we're going to use. And this implies there must be a defined process we have to follow to break the rules. So we've looked and we can see that we can break the rules, but can we break some rules and not other rules? So most coding standards separate the rules into different categories based on the severity. There may be rules that must always be followed. There's no justification for breaking the rule at all, ever. No circumstances can you break those rules. We may have other rules that can be broken, but done via a process. And these rules usually affect the functioning of the code or protect against poorly defined language features. And then we may have rules that apply to things like portability and maintenance, where you can break them, but you don't need to follow the process. But note, it's also permissible for a company to have a process that you have to use when breaking any rule. So a deviation process is a process we can use to break the rules. And this usually involves multiple members of a team, not just the developer who might just decide, I don't want to follow the rule in this case. So where there's a need for a deviation, we must produce documentation to describe which rules are being broken, why they need to be broken, as opposed to rewriting the code in a compliant way, and why breaking the rule will not compromise the safety of the code. So what are the dangers of breaking the rule, and how we assess the risk and any mitigations of the alternative coding we're using. Now, ideally, we'd like to do this before we start the coding phase. So we may know things like compiler limits and hardware access, so we can set up some deviations before. But it may be that while developing and testing the code, we come across reasons why we may need to deviate. For example, compliant code produces less efficient code, and we can't meet timing or memory constraints for our software, and we need to recode the code in a way that breaks the rules. So there's different types of deviation. Project level deviation that applies to the whole project. This may be something related to a compiler feature that's offered. That means we don't need to follow a particular rule. We can have entity-based deviations on specific code constructs wherever they're used. For example, in a way a macro is expanded, or a function call where perhaps we're going to ignore the return value of a particular function call throughout the whole project. And we may also have specific deviations, and these occur at specific places in the code, either an individual line or perhaps an entire function or an entire file. So static analysis tools are really the only realistic way to enforce coding standards. They're quick, repeatable, not subject to opinions, unlike people. And a decent static analysis tool can be configured to hide the diagnostics. So these are the messages that appear that tell you if you've broken a coding standard rule. And where we turn a message off, we can call this a suppression. Usually you can do this globally per entity and specifically in specific areas of code. Different tools have different options to enable this. There may be configuration options, comment-based code suppressions, or maybe you have a graphical view where you can point and click and suppress messages. So to clarify, a deviation is the permission to break a rule, and the suppression is a way to achieve this deviation. Otherwise, you have all the diagnostics in the code, and you have to manually note which ones you are deviating from that you don't need to fix, as opposed to the ones that you do need to fix, which can become very burdensome. So given that we have a powerful way to turn diagnostics on and off through our code base after analysis, how do we match up these suppressions to our deviations? So the global suppression should be configured somewhere in a configuration file, should be easy to find. And if we version control our configuration, we can have an audit trail for that as well. Entity-based suppressions will probably also be in configuration files, but they may also be put in source files. And then the specific deviations are much trickier. They can be located anywhere in the source code base. We should also be careful if we've got any suppressions in header files and look at the behavior of those suppressions and how they flow through into source files they're included in. So we should check our static analysis documentation to know how they work. So reporting on these deviations is essential. We want to know where they're located in configuration files, which configuration file, and in the code, the exact location of them. And for each diagnostic that's suppressed, so there's an actual violation and no diagnostic is shown, we want to know which suppression was used, and we want to be sure that the diagnostic is suppressed because of the reasons stated in the deviation. So if we're allowing pointer conversions because of hardware access, we want to make sure that the violations of that rule are for that purpose only and not for other reasons that someone may have made by mistake or intentionally. We also want to know if there's any redundant suppressions, so suppressions that don't suppress anything, or multiple suppressions in play when a diagnostic is issued. So we may have redundant suppressions that no longer suppress an issue because the issue has been fixed, either on purpose because someone's gone in and addressed it, but they've left the suppression there, or perhaps someone's gone in, modified some code, fixed a bug, and this has caused the coding standard violation to be fixed, or possibly because the code has been modified somewhere else, and that has caused the diagnostic to no longer appear. So when we fix an issue, we should ideally remove the suppression, but sometimes this isn't always possible because you may not notice you have fixed the suppression, so you may end up with a redundant suppression. And the problem with these is during maintenance, we could end up with code and comments in the code that don't do anything, which can lead to confusion if people are trying to read the code. They may not know why a message is being suppressed if it's not being issued. And also comment-based suppressions can lead to clutter in the code. If lots of suppressions are added and never removed, you can end up with lots of comments, which can get in the way of reading and comprehending the code. We may also add some new code that unintentionally breaks the rule, and because the suppression is active, we don't know about it. We could have duplicated suppressions suppressing the same violation twice, so it could be difficult to identify which deviation is being used. And we could decide to remove a global suppression, but there could be a local suppression still active. So you may think that you've removed that suppression, but it could still be active in some area of the code. So a quick talk about legacy code, because we're often reusing code from one project in another code or in the next version of the software. If it's not written to a coding standard, it may have many violations. It may also not have a full set of tests or requirements. So we could say, well, why do we need to fix the coding standard? We've used this code before in other products and we're happy that it works. Well, addressing the issues will improve the reliability, portability, and maintenance. And it also gives us a chance to thoroughly assess the code's suitability in a safety-related environment. But before we start fixing anything in legacy code, we really need a full set of tests. Not necessarily requirements-based tests, but tests that show the code does what the code does. So, for example, vectorcast ATG can generate tests to go down every path in source files and then set the expected values based on the actual values. So this really gives a fingerprint of what the code does. And this is important because if we go and fix coding standard violations, we can rerun those tests and be sure that we haven't changed the functionality of the code. And we should also ensure that we've got 100% code coverage so that we can, if we fix issues in a particular area of code, we know that we've got that covered by the tests. So a plan of action for our legacy code. Well, first of all, we have to fix all the mandatory violations, the rules we're not allowed to break at all. That's not an optional step. We have to do that. And then we can look at the rules that require deviations. And we can look at the distribution of the violations. And if we have lots of violations of the same rule, it may be easier to fix these because it may be a common issue, or it may be easier to create a single deviation to fix multiple rules. If we have many violations of different rules, this is going to be a bit harder because each violation will have to be separately looked at and require a separate deviation. And then we can decide whether to fix or deviate the violations. If we decide to fix them, we should run our tests again to make sure we haven't changed the functionality of the code. And if we're going to deviate, we need to go through the normal deviation process. Then we can have a look at the advisory rules. And these ones we don't have to fix, but it may be useful to look at them and fix some of them. So rules that deal with portability might be useful if we intend to port the code to a different platform. And readability and maintenance ones are useful if we're planning on modifying the code and adding features to the code. So what kind of reporting do we need to sort of prove our compliance? So if we run our static analysis on our code, it should show no issues. So here's my report of my project here, no violations. But did the analysis actually run? Did I analyze all of the files, or did the tool just crash out while analyzing the first file? Ideally, we want to report something, even if there was no diagnostic issues in the code. So this is an example from a PCDIN Plus, which has a message 900, which is issued right at the end of analysis and tells us what happened. So we processed 20 files and got no messages. So we know the analysis completed. So either all of the issues in the code have been fixed or they've been suppressed. And I want to know if they've been suppressed, where they've been suppressed. So we have a suppression report that tells me which rules have been broken and where. And this tells us if the rules aren't in there, there are things that need to be fixed. And every suppression must correspond to the agreed deviations. If there are suppressions, diagnostics suppressed that don't correspond to an approved deviation, then we need to investigate that. And this will make sure that we're only breaking the rules where we've agreed to break the rules. The duplicated suppression report is not really strictly needed for compliance, but it's a useful check for correctness and making sure that we're using the tool correctly. We also want an enforcement report that tells us how we're checking our coding standard rules. And we can use multiple tools, for example, a compiler warnings and a static analysis tool. We also probably want a list of source files we've analyzed to confirm this is the correct set of files that are going in our project, possibly with the version number as well. And then a list of analysis options, so the include directories we use, so we can identify the header files that we used. If we had any compiler defined set that could affect the variant that we analyzed, we'd like to know that as well. A list of all the diagnostic configuration options that correspond with the coding standard, minus the project-wide suppressions. And then we might want some other information, the date, the time, the machine it was run on, tool versions, and so on. So we're going to have a look at a demo shortly. It's a very simple C project. We've got 2 source files and 1 header file. It uses CMake. We're going to look at the code in Visual Studio Editor with the error lens extension. And we're going to do the static analysis with Vector PCLint Plus, and that's integrated with CMake and VS Code to make it really easy to run. And I've also got a report that runs to show how suppressions have been used using the forthcoming diagnostic accounting feature in PCLint Plus. And we're going to use a very small subset of MISRA rules to make it easier to see which messages I'm suppressing. So we'll do some analysis of the code, we'll see some violations, and then we'll add some suppressions, and then analyze and look at the report, add some more suppressions, and repeat that process, adding single violation suppressions, a range of suppressions, and then a redundant one. And each time we'll have a look at the analysis in the IDE and the report. So here we have my development environment, Visual Studio Code. We can see I've got a couple of my source files open here, and I've got PCLint Plus configured to run inside Visual Studio Code with a keystroke, which I've just hit now. And we can see the analysis output has now appeared. We can see the messages here, and they're highlighted in the code using the error lens extension. We've also got a suppression report that we can have a look at. And so this is the basis of a suppression report. It needs a lot more adding to it, but it's just a simple report. So we can see we've got a couple of messages, and perhaps we want to deviate these messages here. So we can add some suppressions to turn these messages off. So let's go ahead and do that. Add a code-based suppression, turn message 9078 off on that line. So we'll save that, and then we'll kick off the analysis again. And we'll see that now the message has disappeared from that line. We can see it's not in here. And we can see we've got one less message here in the report. And we can also see we have a suppressed message in the suppressed messages table in the report. Okay, let's go and add another suppression in. This time we'll go and add one in here to turn the message off for the whole file, or from that point in the file onwards. So we'll go and run PCLint Plus again. And now we can see we have no primary messages because we have suppressed all of them. We can see we have 2 suppressed messages, but we also have a duplicated suppression. And we can click on the messages here in the problems pane to see exactly where those are. And really, the report here is very simple. We could expand this to say exactly what the duplicates are and where they're located, and so on. So let's just go and add in a redundant suppression. So perhaps we'll suppress message line 970 on this line here. And of course, there isn't the diagnostic 970 on that line there at all. And so we now have a message saying we have an unused suppression. And I'll just refresh the report. And now we can see we have a unused suppression in the report here as well. So this shows us how we can suppress messages and get some accurate reporting and messages based on those suppressions. So the summary, there can be legitimate reasons for breaking the rules. For example, interfacing to hardware, using third-party code, and if our software has variants. But we have to do that in a controlled manner, follow a deviation process, documentation, risk assessment. Static analysis tools are the only way to enforce coding standards, and they usually provide options for turning off the diagnostics in the code, either globally per entity or specific locations. We need accurate reporting of these diagnostics and the suppressions. This ensures that the suppressions match up with the deviations. And proving compliance requires lots of documentation, analysis reports, suppression report, deviations, configuration, source files, and so on. So in summary, you can break the rules in a coding standard, but sometimes it can be more work than not breaking the rules. Thank you for your attention during the Breaking the Rules presentation. We looked at when you can break the rules in a coding standard, how to use deviations to do this safely, and how to implement deviations using a static analysis tool, and how to report on the compliance of your source code project. I look forward to any questions you may have in the Q&A session.